for this first question. I guess the algebra is something like, if you're in an arithmetic series, it means that there's a common difference. So x is equal to 1 plus that difference, and 4 is equal to 1 plus twice that difference. Okay, so difference plus d, and difference to get from there to there. That's just what an arithmetic series means. Okay, d is so the common difference is, so solving this equation for d, I can get d is 1.5, and then putting that back in here, I think I get x is 2.5, 2.5. So similar looking algebra, I suppose, for this second part. The rule for being in a geometric series is that you multiply by a common ratio to get from one term to the next. So x is 1 times r, and 4 is 1 times r squared. Okay, and solving the second equation gives, now some people in the chat have been very careful, and so this is r is plus or minus 2, which is fantastic. In fact, because r is equal to x, that means that x is equal to plus or minus 2. So it's this geometric series, and this is why I set this question. There's this geometric series that goes 1, minus 2, 4. That is a geometric series where the common ratio is allowed to be negative. And if your common ratio is negative, then the terms of your arithmetic progression will flip signs as you go up like that. Okay, arithmetic progression. I wonder what happens if you've got 3 numbers. Can you have 3 numbers like A, B, C that are in an arithmetic progression and also in a geometric progression? Can you have both? So there are examples that work. 0, 0, 0 is the first one I thought of as well. It's a bit cheeky. These are in an arithmetic progression. The common ratio is, the common difference is add 0 each time. They're also in a geometric progression. The common multiple is multiply by 0 each time. There are some other ones as well though. Some people in the chat have pointed out that you could have any 3 numbers that are the same. So 999 is an example of an arithmetic progression, plus 0 each time. And it's also a geometric progression, times 1 each time. And I think some people have claimed that this is sort of all of the solutions in a way, like not just 0 and 9, but any number repeated, A equals B equals C. I thought I'd do a quick little proof of that. Okay, so if A, B and C are an arithmetic progression, so this is the 2 things that I've given you to think about. If A, B and C are an arithmetic progression, then it means that there's a common difference. So I suppose we could write B is A plus D and C is A plus 2D for some D. And over here, then it would mean that B is A times R and C is A times R squared for some R. Okay, and then the question is, can we try and solve anything about A, B and C as a result of that? So we could use this to work out R. So this first equation says that R is B over A. That's quite interesting, because then when I plug that in over here, I could get that C is B squared over A. That's quite interesting. So that's a relationship that must hold between A, B and C. Whereas over here, I can rearrange this one to say, I think A plus C equals 2B over here. So I've got these 2 different relationships that must hold between A, B and C. Okay, one of them says that B squared is equal to AC, and one of them says that 2B is equal to A plus C. Can we have both of these at once? And my aim here is to show that this implies some relationship between just A and C. I'm going to try and eliminate B from these equations. Okay, I should say, when I first started doing this, I was trying to prove that all of the numbers were 0, because I hadn't spotted that you could have 111 or 999. So I was trying to prove, I was trying to solve these equations to prove that they were all 0. I was surprised at the end, but you know, we're making progress towards trying to solve these. That's how I'm thinking of what to do next. So eliminating b, I thought about squaring this second equation. So I'd get 4b squared is equal to a squared plus 2ac plus c squared. But I know b squared is ac. So then I can subtract that off and factorise that, and I get 0 is a minus c squared. So that tells me that a must be equal to c. And then it's not much work to say that if a is equal to c, so this thing 0 is equal to a minus c squared. If a is equal to c, so going all over the place, sorry, but from here, a is equal to c, and if a is equal to c, then because a plus c is to b, b is also equal to a. So all three numbers are equal. Okay. Here is these terms are in a geometric progression, and separately the other terms are in a geometric progression as well. So the sum of the first two n terms is going to be the sum of the first n green terms and the sum of the first n blue terms, or the sum of the first n even terms, the first n odd terms as well. So then the question becomes, can we do the sum of the first n terms of a geometric series? And that's on the maths syllabus. So let's be really careful. So if I want n terms of 1, 2, 4, 8, if I want n terms of that, I'm doing the sum of the first two n terms, but only n of the terms are in this geometric progression. 1 plus 2 plus 4 plus, I have to think really carefully here. I think this is 2 to the n minus 1 at the end, so that there are n of them. This is 2 to the 0. This is 2 to the 1, but it's the second term. So the nth term will be 2 to the n minus 1. Ugh, right, okay. Anyway, this is 2 to the n minus 1, I think. And I want n terms of 1, a half, a quarter, and so on. And I'm going to concentrate for this one as well. 1 plus a half plus a quarter, and so on. Plus, now the nth term is going to be 1 over 2 to the n minus 1, I think, because it's 1 over what the other geometric, 1 over what the other geometric progression was. And when I add those up, I get, what do I get? Is this 1 over 2 to the n? 1, 2 to 1, 2, 1, 2, 3, 4. Yeah, n minus 1. Okay. When I add all of those up, I think I get 2 minus 1 over 2 to the n minus 1. Okay, so adding these two things together gives me a. 1 and a 2, making a 1 in there as well. So this question has these different parts, and the bit at the start seems to be a sort of nice friendly way in to check, do you understand what this equation means? So when it says for n bigger than or equal to 3, there's this relationship, and we've given you an example to show where n is 3, this is x3, this thing here is x2, and this thing here is x1. So to work out x3, we do 2 times x2 minus x1 plus 1, which is 2 times 3 minus 1 plus 1, which is 6. Okay, so I'm going to write out what x4 is by using n equals 4. So it's going to be 2 times x3 minus x2 plus 1. Okay, and we know what those values are. That's 2 times 6 minus 3 plus 1. 12 take away 3 is 9, plus 1 is 10. Fantastic. Okay, and then x5 is going to be 2 times x4 minus x3 plus 1, which is 2 times, the previous thing was 10, x3 was 6, plus 1, that's 15. Okay, brilliant. So our sequence so far has gone 1, 3, 6, 10, 15. Okay, so what do we know? We want x1, if this formula is true, then we want x1 to be a plus b plus c. We want x2 to be a plus 2b plus 4c. And we want x3 to be a plus, when n is 3, this will be a plus 3b plus 9c. How do you write a b? There we go, 3b plus 9c. Okay, but we know the values of x1, x2 and x3. We know that these are 1, 3 and 6. Okay, fantastic. So if this is going to work, then we need these three equations to hold true. So now we've got three simultaneous equations. And I'm sighing a bit because we can solve simultaneous equations. It's a bit of work. We're going to have to do some stuff to sort of eliminate equations. Eliminate A maybe first. I'd go for A first because it's got this common coefficient of 1 in each of these. I'd do like subtracting equations from each other, I think probably. So I'd do second equation minus the first equation to just get rid of that A. So I'd get something like 2 is B plus 3C. And I do third equation minus the first equation to get something like 5 is 2B plus 8C. Yeah, 8C. And maybe I'd subtract these as well to get rid of some B's or something like that. What am I going to do? Am I going to do this? I feel like I'm talking myself into doing this equation, solving these simultaneous equations, which is more maths than I intended to do. But there we go. Solve that. I get C is 1/2. I've got B is 2 minus 3 over 2 is 1/2, and A is 0. I think back from that first equation. Of course, simultaneous equations, eh? We'd like to know what the smallest n is, such that xn is bigger than or equal to 800. Interesting. Okay. Or said in different words, what's the first triangle number over 800? Which is a bit of a tough question. I suppose the good news is that this equation, as you increase n, it keeps getting bigger and bigger. So we can just look for sort of like the first time when it goes over 800, and it's not the case that it's sort of jumping around randomly and it's going to be a really hard search. We kind of expect it to go up until it's bigger than 800 and then stay bigger than 800 after that. So I think my plan is to sort of try and solve what if I want n squared over 2 plus n over 2 roughly equal to 800. When does that happen? So if I can find roughly when this happens, roughly when it's about 800, then I'll have a good sense of when it swaps from being less than 800 to bigger than 800. Okay. If n is quite big, then this thing on the left is roughly n squared over 2 on the left, because n squared is much bigger than n if n is big. So I want n squared to be roughly equal to 1600. So I expect n to be about 40. And now I'm going to go and check. I'm going to go and check near 40. And I've been very sort of hand wavy roughly equal to, so it might be 37, 43, somewhere in between. So if n is 40, that's right. So if n equals 40, then n squared plus n over 2 is 1640 over 2 is 820. Okay, that's bigger than 800. Should also check if n is 39, then n squared plus n over 2. I suppose I go and work out 39 squared. Do I want to do that? Not really. Oh, is this 39 times 40 over? Yeah, this is 39 squared plus 39 over 2. Or do some arithmetic and shortcut it a little bit to say that this is equal to 780. Oh, it's 40 less because we've just added 40 between the triangles. Okay. Right, okay, so I think that means that when n is 39, we're just less than 800. When n is 40, we're just bigger than 800. So I think this n is 40 is the smallest n, such that xn is bigger than or equal to 800. In fact, it's bigger than 800. Okay. We can use this relationship to work backwards from yn all the way back down to y1. So for example, y1 is 1, and then I'll use this equation for y2. y2 is equal to y1, which is 1, plus 2 times 2, which is 4. And then y3 is going to be 1 plus 4 plus, and then 6. Similarly, y4 is going to be 1 plus 4 plus 6 plus 8. And yn is going to be 1 plus 4 plus 6 plus, all the way up to 2 times n. Okay, so I can recognise that other than this first one, this is an arithmetic progression. So here we are. We start at 4. We go up to 2n. The first term is 4. The common difference is 2, and I need to be able to add up the terms of that series. If you add up the terms of that series, I think you get n squared. So there are, I'm going to try and do it live again. There are n minus 1 terms, and the average of the terms is 2n plus 4 over 2. So if I add those up, I get n plus 2 times n minus 1 plus 1, which works out to be n squared plus n minus 1. Let's put that over here. N squared plus n minus 1. Okay, multiplying out some brackets. Okay, so now we've got xn is equal to n squared plus n over 2. Yn is equal to n squared plus n minus 1, and there's this last part of the question to say what's the approximate value of xn over yn, and when n is very large. So when n is large, xn is roughly equal to n squared over 2, or I suppose the difference is still n over 2, but the biggest bit of xn is this n squared over 2, and the biggest bit of this yn is n squared. So xn over yn is equal to n squared over 2 plus n over 2, n squared plus n minus 1, and that's going to be roughly equal to, forget about the n over 2, that's not as important as this n squared over 2. This is going to be like a million squared over 2 is so much bigger than a million over 2 when n is a million. And similarly down here, when n is a million, who cares about this n minus 1? N squared is the big news over here. Okay, so this is going to be something like n squared over n, which is 1/2 when n is large. I tried some small numbers. So when I say is find a pair of positive integers, I don't have any idea on how to solve equations like this in general, but I'm going to try some small numbers. You know, I tried normal stuff like 1. Trial and error. People have got 3 and 2. Oh, 3 and 2. That's 2 votes for 3 and 2. Hang on, let's check that live on stream. 3 squared. So 2 times 2 squared is 9 minus 8. That is 1. Second part of the question. We're now going to make these numbers into sequences. The new terms of the sequences, this is a little bit strange, are going to be defined in terms of the previous value of each of these sequences. So xn plus 1 is going to depend on xn and yn. And yn plus 1 is going to depend on xn and yn. And it's got these numbers a and b. When I saw this, I thought, I'm just going to plug it in and see what happens. So I'm going to take xn plus 1, I've got this equation, I'm going to plug this in here. I've got yn plus 1, I'm going to plug this equation in here. And you want this to equal this? Fine, off I go. I can work that out for you. So I can do 3xn plus 4yn squared minus 2 times axn plus byn squared. I'm going to multiply this out and compare coefficients. I want this to be equal to this. But what I've actually got is 9 minus 2a squared xn squared plus, and then horror, I've got a load of these cross terms, 24 minus 4ab xn yn, and then I've got some 16 yn squareds over here, minus 2b squared yn squared. Okay, so I don't really want this middle term at all. I sort of want AB to turn out to be 6. And I want 9 minus 2a squared to be equal to, so I want, comparing coefficients, I want this. So I want 9 minus 2a squared to be 1, and 16 minus 2b squared to be minus 2. So I suppose I want A to be something like 2 to solve that, and B to be something like 3 to solve that. I've been told to use positive values of A and B, so I'm not worrying about these square roots that I'm taking. Oh, and then luckily, 24 minus 4ab is 0. So this does actually work. I do actually get all 3 coefficients to work out. Okay, so if I plug that in, I get the just the coefficients I want when I use A is 2 and B is 3. I think that might be the only solution with A and B both positive. Okay, here's the point of the question. if x1 squared minus 2y1 squared is 1, and when you follow these rules, you can find these new integers, xn plus 1 and yn plus 1, and they also satisfy new thing squared minus 2 times new thing squared is equal to, well, the same value that x squared minus 2y squared previously had. So if xn squared minus 2yn squared is 1, then xn plus 1 squared minus 2yn plus 1 squared is also 1, because it's equal to the previous thing. Okay, so this says as you generate these numbers through this sequence, according to these rules, you get new examples of solutions to the equation x squared minus 2y squared is 1. I think that's pretty cool. So my plan for part 3 is to use this previous rule to generate new values. Okay, so let's work out what happens as we generate new values out of this. So we start with, what did we start with? We started with x1 is 3 and y1 is 2. So this is n equals 1. And then when n equals 2, this is going to be my x's, these are going to be my y's. For n is 2, I'm going to work out my new xn. So my new value of x is going to be x2. That's going to be 3 times xn plus 4 times yn. So 3 times this plus 4 times this is 9 plus 8 is something huge like 17. And over here we're going to have this is going to be a times xn plus b times yn, and I've decided that a is 2 and b is 3, so I want 2 of these and 3 of these. 6 and 6 is 12. Aha, that's the 1712 example that somebody gave us earlier. When n is 3, I want to do same process again. I want to use these rules to generate a new example. So I'm going to do 3 times xn is 51 plus 4 times 12. 51 plus 48 is 99. And over here I'll do axn plus byn is going to be 2 times 17 plus 3 times 12 is 34 plus 36, which is 70. Okay, here's an example with two numbers bigger than 50. So with 99 squared minus 2 times 70 squared is 1. And that's actually true, which is amazing. Final part of this question, using values of a and b found in part 2, so we're generating this new series of numbers that satisfy x squared minus 2y squared. This is going to be true again and again and again for all the new values of x and y that we calculate. What's the approximate value of xn over yn as n increases? So xn and yn both are both positive, and they get really large. And they get really large because I suppose each is more than twice the previous number. Whenever you do this rule, you're doing 3 times the previous value plus some more stuff. So xn more than triples each time. And yn is 2 times xn plus, I think this was 3 as well, so it's more than tripling each time. Xn and yn are both really large for large n. So we've got x squared minus 2y squared equals 1. X squared and 2y squared are both massive, so we must have x squared roughly equal to 2y squared. These things are both like a million billion or something, right? And the difference between them is 1. These things are both huge and roughly equal if they're each massive, and the difference is only 1. If x squared is roughly equal to 2y squared, then I think x is roughly equal to, just do some algebra on this, root 2y. So x over y is going to be about root 2, I think. Oh, they're both positive. Everything's positive for this.